All right, let's look at the practice exam 3, problem number 3. All right, so first we try to sketch the feasible region. Right, so first I'm going to turn all these inequalities into equalities. So you have x minus 2y equal to 0. All right, this guy becomes 2x minus y is equal to 6. All right, and these are non-negative constraints are easy. Right, so let's do the non-negative constraints. Right, so x is greater than or equal to 0 means that it has to be to the right of the y-axis. So I'll just indicate it with that. Right, so we took care of that. So y is greater than or equal to 0 is it has to be above or on the x-axis. So took care of that. All right, then we're gonna look at these. Right, so first equation, so you have x minus 2y equal to 0. So then I'll just solve for solve for y. So add 2y to both sides to get x equals 2y. Then divide through by 2. Right, that way you can have y equals 1/2 x. Right, so this is going to be just a straight line, of course, and slope is 1/2 and y-intercept is 0. So you can see that it's going to go through the origin because y-intercept is 0 and slope is 1/2. So you go to the right 2 units, go up 1. So it's going to look probably something like this. Right? Then we have to pick the size. So this is just a straight line. Maybe I'll extend that, and maybe I'll extend that. Right? All right. Then we have to pick the size. So since I usually use the origin, but origin is right on the border, so I'll pick something else. For example, I'll probably use say 0, 5. Right. Right. Plug in 0 for x. And 5 for y. So 0 minus 2 times 5 is negative 10, which actually satisfies this inequality right here. So we have to pick the side that has 0, 5 in it. So in this case, we have to pick the upper half plane. So I'll do it like that. All right. And how about the second one? So you have 2x minus y equals 6, right? So from here, you can find the x-intercept, right? So what would be the x-intercept of that line? Right, x-intercept is going to be, so we set y equals 0, so you have 2x equals 6. Right, then divide through by 2 to get x equals 3. Right, so x-intercept is 3, and a y-intercept would be, right, y-intercept, to set that equal to 0, so it's going to be negative y is equal to 6. Then we can multiply by negative 1 to get y equals negative 6. All right, so it's going to be a straight line going through x equals 6. So here's the x-intercept, and a y-intercept is going to be, so it's going to be negative 6. So I'm going to extend it. So negative 6 would be somewhere around here, negative 6, right? Well, you can see that the slope is going to be 2, so we can kind of make, so we're going to have a line going like this. So slope is 2, so make sure that I go through the right points. All right, something like that. All right, then it goes through there. All right, then we have to pick the right, pick the half plane, right? So in this case, I can use 0, 0, right? So plug in 0 here, plug in 0 here. 0 minus 0 is 0. It's actually satisfied this inequality. So which means that we have to pick the half plane that contains 0, 0, which is the upper half plane. All right. Combining all four inequalities, you can see that it has to be to the right of y-axis, above the x-axis, above this borderline, and above that line. So you can see that the feasible region is going to be right here. Right? Right? And this guy actually keeps on going. All right. Then what we need to do is we want to maximize and minimize this objective function right here. Right? First, I'm going to rewrite objective function as y equals x minus z. Right? So you can see that negative z is basically the y-intercept. So this guy is the y-intercept of the objective function line. And the slope is 1. Right? So 1 is a slope. Right? So you can visualize a family of objective function line with slope 1. So it should look somewhat like this. So slope 1. So something like that. So you have a family of curves, straight lines, objective function line, which looks kind of like this. All right. Then we want to, let's see, because of this negative sign, we normally try to push it up to maximize and try to push it down to minimize. And because of this negative sign, we have to reverse that. So we want to push the objective function down to maximize and try to push the objective function up to minimize. All right, so let's try to maximize it. All right, so you can see that you have a line like that, and you want to push it down as far as we can without going out of the feasible region. So you can see that the farthest you can go would be something like this. Right, maybe I should use a different color. Say, how about this? Right, this would be the lowest we can go without going out of the feasible region. Right? Right, so that's going to give you the maximum. Right, and you can see that the only feasible point that's on this feasible point that's on this objective function is that point, which is 4, 2. Right, so the z is going to have a maximum value when x equals 4 and y equals 2. So maximum value is going to be z is equal to, right, x is 4, so 4 minus y, so it's going to be 2, right? 4 minus 2 is 2. So this is a maximum value, right? But on the other hand, minimum value is going to be, right? So you can see that we want to push this objective function as far as possible, but this is an unbounded feasible region. So this guy actually keeps on going forever upward. So the objective function can be pushed up forever, right? So therefore, minimum actually does not exist. Right? Right, that's it. I hope that this was clear.